I'm going to talk about two contexts where some assumption on a measure implies an apparently much stronger property. Let's recall our Radon-Nikodym theorem, which states that if you have a sigma finite measure in Rn, which is absolutely continuous with respect to the Lebesgue measure, which I'm going to denote with dx, then the measure comes from a weight, a density. We can integrate a locally integrable function to obtain mu from the Lebesgue measure. But what I'm more interested in here is a corollary to this. There exists, so under these assumptions, for every epsilon positive, there exists a delta positive such that Lebesgue measure of a set less than delta implies that the mu measure of the set E is less than epsilon. And this follows from what is called the absolute continuity of integral. If you have an integrable function, then its integral over very small measure sets will also be a small quantity. Now, if we put these together, what we are really proving is that for a sigma finite measure, assumption that measure 0 implies measure 0, this assumption implies a quantitative version where you don't have to just work with 0 but epsilon delta. So as well, you could turn this as into the definition of absolute continuity because it just follows from it anyway. So let me introduce a new context where a similar thing happens. The context of A infinity measures. So we again are working on our N. We have a Borel measure mu. We also assume that measure of every ball is positive and finite. Now, just before recording this video, I had to ask myself, do I actually need to start with the assumption of doubling, or does it follow from the property? And I'm pretty certain that it does follow from the property that I'm about to define, but just to be sure and not make silly claims, let's start also by assuming that mu is doubling. If you take a ball of radius xr and you double it, so take double that radius, then this measure is governed by a quantitative multiplicative constant of measure of ball x and r. So for C, independent of the ball, independent of its center and its radius. So if a measure satisfies this, we call it doubling. So mu is doubling. And this is the property that I'm not sure if we can just drop from definition and follows as a consequence of it. But again, anyway, that is not the main point, so let's just assume it to be safe. Now we say a measure, a doubling measure on Rn is an A infinity measure if for every epsilon positive there exists delta positive such that if relative measure of a set is small, then the relative measure in the mu is also small. So what is the relative here? That means for every ball for every ball in Rn, and every measurable subset E of the ball. So it's very easy to decipher, but let's draw some pictures. They never hurt. So here is a ball, and then you have some subset E, and the relative measure of E is really small. So this actually could be a very large number if your ball B is also very large, or a smallness of E could be way smaller if you already are looking at the microscopic ball. So this is kind of a scale invariant requirement on the set E. And then what this says, that if Lebesgue measure sees E as a very small percentage of the ball, then the new measure mu also does the same. So that is our definition of an A infinity measure, and it has very important geometric motivation behind its definition, which I'm not going to enter, at least in this lecture. And now I can state the apparently self-improving property that I mentioned. So there is a theorem that says, suppose, let's just be precise with assumptions, suppose mu is a doubling, which includes this positivity and finiteness on balls, measure on Rn, and there exists some epsilon positive and there exists some delta positive, such that measure of E divided by measure of ball less than delta implies, let's actually call them zeros because they are specific ones, measure of E over measure of ball is less than epsilon 0 for the same collection. So for every ball B and every measurable set E inside B. So these are all assumptions. Suppose that we have a measure that satisfies this for two specific values of epsilon and delta. Then a mu is actually an infinity measure. That means for every epsilon positive, there exists a delta positive with the same thing, that this less than B implies measure of E over measure of ball less than epsilon, blah blah, for every this and that. And that is analogous, in my opinion, to what happened earlier. We assumed that measure 0, let me use red here to just compare again. So measure of E 0 implies mu measure 0. From this we concluded that measure less than delta implies measure less than epsilon. For every epsilon there exists delta. And here similar thing happens. If there exists positive values where this happens, then it happens for all epsilon. And again, it may be now a good exercise that whether this would hold without a priori assuming doubling. Maybe in the theorem it is needed, but I'm pretty sure in here, if you drop this doubling here, then you conclude it as a consequence of this epsilon delta property. An easy lemma. From this definition, we see that every A infinity measure is in particular absolutely continuous. Well, this definition is a stronger form of absolute continuity, because if measure of E is 0, then you immediately get from this condition that the mu measure is also 0. So it's absolutely continuous. So this mu comes from a weight, w dx. So there's this weight, and now the message for those familiar with the literature is that this A infinity weights, basically the infinity measures as a result. So these W's are simply the union of all AP weights, P bigger than 1. Before this, let me say, all the definitions of A infinities that I had seen was through this definition, which is not that intuitive because, for instance, we never look at LP spaces and say, let me just take union of all of them or something like that. And if you look at definition of AP weights, it's very technical. There wasn't that much kind of motivation and geometry why we should look at such weights. Then I learned that actually you can just work with measures a priori, and then the statement, one of the equivalent conditions of being a infinity weight is that the measure coming from this weight satisfies this property, which is then very much geometric indeed. So let me just, for completion here, add that where AP are the famous Muckenhoupt weights, and they have their rich background of their own and still subject of study, including in metric measure spaces. Yep. So, but the point again, there's so much here we could talk about. We can go in a million different directions. But my message was this kind of amazing idea that with measures, sometimes strange things happen, that something seemingly weaker implies a much stronger property. If you have any comments, or if you want to hear more about any other aspect of these that I just mentioned, let me know in the comments, and maybe I can make more lectures on those specific topics. Recently, I have been obsessed with and been reading everything out there about weights and infinity weights, Muckenhoupt weights, and the Sobolev spaces that come from these weights, and the motivations behind these. So I can say that I definitely have more to say about these, but I would like to hear from you first. Thank you so much, and have a great weekend.